Hello, this is Jack Jackson. Today we're going to be talking about how we can assess whether a data set is normal or not, whether this data set likely came from a population which has a normal distribution. Specifically, the technique we're going to be talking about is a normal probability plot. Now, there are actually several types of ways of assessing normality, and there's some hypothesis tests for this that we could talk about, but this is a pretty straightforward way of assessing this visually. So there are several formal and informal methods. We're going to be looking at this one particular method, the normal probability plot. Now, I'm working from a set of notes here which are going to be posted on Blackboard along with just following this video. So you'll have the notes there to follow along with. So I'm going to do that rather than a PowerPoint this time. So how do we start? Well, we start by getting some data, and here's just some sample data. This has 20 data points, and I had typed these into an Excel data sheet and arranged them in increasing order. So I used Excel to sort them. The data originally was probably not in increasing order. And then I give them a rank. So the first one, the lowest one will be rank 1, the next lowest one will be rank 2, and so forth. And so we rank these, which means put them in order and assign a number 1 to 20 based on their position in this list. Now, the basic idea of what we're going to be doing here is we're going to say, well, if this were from a normal distribution, and we choose a random set of 20 data points, the relative position in this data set should agree with a probability that would go with the z-score for that data point. So let's see if we can see what this means by doing it for this data set. So we want to basically take this number 340 and we want to find a probability associated with that. We want to find its relative probability. Now, one of the problems that we run in right off the bat when we're using a continuous normal distribution, it is continuous, whereas we have a discrete data set. So we have to kind of take into account the rounding off. So anything from 18.5 to 19. Almost up to 19.5 is going to round off to 19. So we want the probability that we're less than 19, and that will actually go up to 18.5. So we're going to find a relative cumulative relative probability associated with this number based on its rank. So in other words, if we want to try to find the one that goes with say 340 here, we're going to go for not 19 but 18.5 and take 18.5 over 20, and that's going to be the relative frequency we want to work with. This adjusts for the fact that we have a continuous distribution on the normal side, but on this data set is actually discrete. Okay, well, anyway, what's the basic formula? The basic formula is take the rank minus a half and divide by n, and that's going to give us a relative frequency or a probability that we want to use. N is the sample size, how many data points we have. R is the rank for each data point here. And so for each of these ranks, for each of these numbers here, we're going to take its rank, subtract a half, divide by n. That'll give us a probability associated with it. So now what we want to do is we want to say, well, if it was that probability, what would be the z-score of a number from that probability if it was from a normal distribution? Okay, so what we want to do is we want to do an inverse normal of that probability. Okay, and that'll come up with a z-score from a standard normal. So that's just an inverse norm of p. Of course, p was r minus 0.5 over n. So we're going to use this formula, inverse norm of r minus 0.5 over n. Now this would be the z-value from something with that probability if it were from a normal distribution. Okay, so that cumulative probability. So we're going to do that, and we come up with this table here. So we want to take the rank. We have our data here. We put it in order. We give it a rank. We take the rank, subtract a half, and divide by n. So 1 minus 0.05 is 1 minus a half is 0.5, divided by 20, and then do the is 0.025, take the inverse norm of that, and we get a z-score of negative 1.95996. This would be the expected z-score if this came from a normal distribution. And we do this for each one of these. What I'd like for you to do now is pull out your calculator and just make sure that you understand these numbers in this table. Remember, these data is what's given. You can clearly see they're put in order and the ranks are here. I think that's going to be pretty easy for you. But I want to make sure that you understand how to get these cumulative probabilities and z-scores using the formulas above. In particular, how to get this last number over here, because that's the one we're going to be using. So use this formula right here, inverse norm of r minus 0.5 over n, and apply that to each of these ranks and see if you can come up with a few of these on your calculator. If you do that, check a couple of these and make sure you understand what's going on, and come back when you're ready to go on. So press pause now. Okay, now that you're back, we can check these. Hopefully you've done these. Now, it's pretty easy to do this in Excel. Here are the formulas that you type in to get the table that'll look like this up here, and that's actually how I did this. I did this in Excel and then copied it over to a Word file, and eventually you'll have a PDF of this. So here's our data, which I sorted it in order. Okay, and then I did the ranks. So first of all, how do we do that? Well, we just type our data in. We can highlight the data here, and then go over here. It's off the screen right here because I narrowed the screen down. But if you go over here a little bit, there's a sort button, and you can go down there and select sort in ascending order. So it'll put these in ascending order. Then I just type a 1 here in cell A2. In this cell A3, I type 1 plus, or start with an equals 1 plus A2. That'll make it a 2. Then copy that and paste it down in these cells below, all the way to the end to 20 data points. Now, to find P, I started this one in cell C2 and said equals, and I clicked on the cell, parentheses, then the cell A2, clicked on that, minus 0.5, divide by, and G3 was the count. In this case, there are 20 data points, so I could have just said divide by 20. But I did make this spreadsheet a little bit more dynamic because I let this data run all the way to, all the way down to cell 296. There's nothing below the data below this cell at 21 here, row 21. But if I were to add data below that, it would count it here, and that would be our data value. Of course, I want to absolute reference that. I want this to stay column G and stay cell 3, G3. So I put dollars in front of the G and the 3. Then when I copy and paste, notice it will automatically adjust the formulas here. And I have it where it's showing the formulas. And if you show the numbers, then of course you're going to get these numbers right up here that are in the table. Then I just do norms inverse of C2 to get what we need there. I think later on down the line I've got something. Okay, norms inverse. And then continue on. So if this data is from a normal distribution, then these z-scores that we have right up here are based on these ranks. That would be what we would expect. But on the other hand, we know what the actual z-score is of these numbers because we can find the mean and standard deviation, which I can do average here and standard deviation in Excel, and these come up with certain numbers. Okay, and we can use that to do this. Now I want to, for reasons I'm going to show you in a little bit later on, I want to call the data values here y, and then we'll call these guys z's. So we're going to look at the y's and the z's. Well, the z is y minus y bar over s. It's data value minus the average of the data values, the mean of the data values, divided by the standard deviation of the data values. It's from a sample, so that's y bar and s, not mu and sigma. Now, this is just a linear function. If we could solve for y, we get s times z, and then add y bar, And we get this nice little formula here that y equals s times z plus y bar. So if we think of z as our x value and the y as our y value, our data values as y's, and our expected z's as x's, then we have a nice linear equation here. And not only is this linear, the constants have some meaning. The y-intercept is y bar, which is the average of the data values, the mean. And the s is the slope here, and so the slope of this line is the standard deviation of the data set. So we see this linear equation. So what it says, if we take a scatter plot with the x's being these z-scores, these expected z-scores that we just figured out, and the y's being the actual data values here, here's the table down here with the x's and y's, like that, then we can graph this as a scatter plot. What should we expect? Well, we should expect that line. Well, not exactly that line, because it's approximation. Even if we had the data were actually randomly drawn from an exactly normally distributed population, we still wouldn't expect just a random sample to exactly fit on this line. But if it comes from randomly from a population that has a normal distribution, the graph should be approximated well by this line. So I just used Excel to do the normal probability plot by just doing a scatter plot. And I get these dots here. And I clicked on this and added a regression line, which is called a trend line in Excel. And I came up with this equation. And notice that the y-intercept, 252.3, really is exactly the mean of that data set. And the 52.038 is close to the standard deviation, which is, it's actually off that just slightly, but it's very close to that. The R-square is 0.972, very close to 1, so this is a very good fit. Also, looking at this, we see that some of the data points are below, some are above, and there's no clear pattern to that. If you have a bunch below here and a bunch above at the end, that could indicate some pattern that's not completely normal. If they're all off on one end or the other, or there's one that's way off, that might be an outlier. But in fact, they're all fairly close with no real discernible pattern, so there's a good chance that this comes from a normal distribution, and so that's our conclusion. Notice the x values here are the z-scores, and the y values are actually the actual data points. Where this crosses the x-axis right there, the y-axis, excuse me, then that's going to be the 252.3, 0 comma that, so that is going to be the mean. Slope of the line is approximately the standard deviation. So what do we want to do in general? We want to test for normality. This is the process we need to do. If the graph you get is approximated well by a straight line, we conclude that the data is likely from a normal distribution. And if the line does not fit well, or there's some kind of clear pattern to the data that's not linear, then we conclude the data is not from a normal distribution. Why do we want to do this? Well, it turns out that many of the things that there are lots of times that we would like to have a normal distribution, or that we actually need a normal distribution in order to go forward and to do our testing, or do whatever we want to do next in our statistics. Particularly when we talk about Unit 4 in inferential statistics, it's going to be very important for us to start out with something that's from a normal distribution in some cases. In other cases, we're okay if we just get the distributions of sample means to be normally distributed or approximated well by that. So let's do this again, and we're going to do this again in Excel. And here's some real-world data. So I have an Excel spreadsheet here. I downloaded a bunch of data about the United States presidents in order. This is the order that they were inaugurated. George Washington first, John Adams, Thomas Jefferson, and so forth. This is the year they took office and the year that they left office, how many years they were in office, what's their birth state, their birth date, the date of their death, the religion, what date they were inaugurated at the beginning of that term, and then the age that they died. And I want to specifically focus on the inauguration age for now. Okay. Now I want just some of them were inaugurated more than once, 4 times for Franklin Delano Roosevelt, but a lot of others were inaugurated twice, and of course several were inaugurated once. So we want their age at their first inauguration. Now this does give us a little bit of a problem with old Grover Cleveland, because his first inauguration here was at age 47. Then Benjamin Harrison was president, and then then he won another term, re-election, but with a term in between. He's only one happened. So we're actually going to throw out this data point of 55, and we don't need that because we only want their first inauguration if they were inaugurated more than once. So we're going to take this data minus that 155. So you'll see Barack Obama referred to as the 44th president, but he's really only the 43rd person to serve in that office. Because for some reason people count for this, because there's one in between, a lot of people will count Grover Cleveland twice, but where they don't count, for example, Roosevelt 4 times. Okay, so if I come over here, and this is in the order, actually right now, the only thing I'm looking at is their age at inauguration. So what I do is I copy that, and I'll just go ahead and do it here, and then paste it here. Okay, and then I take this data here, and I'm going to put it in order. So I'll go over here to sort and filter, sort from smallest to largest. I've got what I want, and I want to sort that. Now these no longer, maybe I should these no longer line up with the names over here. Okay, and so the rank, so here's their ages here in order again. Whoops. Okay, I pasted them here. And I want to find the rank, so I just type in 1, and then below I type, the easiest way is equals 1 plus the one above, and then copy that and paste it below all the way to 43. I have, in this data over here, I have taken out that second Grover Cleveland, which was let's see, I guess I've taken it out over here as well. Took it out first, and then when I copied it from the other page, I pasted it and took that line out. Okay, now I need to find the expected z-score. One way is norm.inverse of open parentheses twice the cell to the left, which is the rank, minus 0.5 parentheses, divided by 43, because there are 43 of them. I could have had it do a count for me if I want to make this dynamic. I probably should, because if I add the next president after President Obama to this list, then I'd want it to be able to update without having to redo everything. But I'll just leave it 43 for now. And of course the mean 0 and standard deviation 1, and put that there, copy that and paste it below, and we get the whole list. So also over here I've figured out some descriptive statistics. This is the formulas, these are the formulas that I'm using. So min A3 to A45, C3 to C45. Well, actually it's C, not A. So these probably should say C instead of A, because that's where I've got the data. I'm not going to fix every one of these right at the moment, but you'll see these all should be talking about C's instead of A. Okay, but anyway, over here you'll see that it's actually right. You can see the formula up here and the thing up here. And so we can see there's our 5-number summary, our quartiles. Our mean is 54.6. That one's going to be important for us, what we're doing now, and our standard deviation about 6.35. Okay, now to get a scatter plot, notice I've lined these up with X. This is X's and these are Y's here. So I highlight my data like this. X is on the left, Y is on the right. And then I go to Insert a Scatter Plot. And there we have it. I don't need that, so I can get rid of that. I can, if I want to, I can click on a data point. Let's right click on it, and I can say add a trend line. This is going to add a, let me just display the equations there. This is going to add the linear regression line to it. Okay, and if you look, that's pretty close. Now we could also do some formatting. Most of that's up here under either layout or design. A lot of it's under layout, and you can select things like axis titles and chart titles and background areas and things like that. I have this already done here where I've kind of made it look a little prettier and added the appropriate labels on my X and Y axes. I have my regression equation up there, information, and so forth. And so we see this data is quite normal. There's no particular pattern to the points that are above or below the line. The points are pretty close to the line. We have a really high R-square value, nearly 99%. And so this is a very, very good fit. And basically, there's our data. And this tells you the process. Get the rank data, I set in column D. Original data in column A, starting with cell A2. Copy and paste it in column D, starting with D2. Select that column, sort it from lowest to highest in column D. Get the ranks in column B. These may be different columns than I had over there, but this will work. Enter 1 in cell B2, 1 plus that equals 1 plus cell B2 and cell B3. Copy it and paste it below. You saw me do something like this. Find the exact expected values, and this is one way to do it with norm.inverse of B3 minus 0.5 divided by 43, 0, 1. 43, of course, should be whatever your sample size is. Copy and paste that below. That gives us our expected Z's in column C. Column D is the original data. Highlight that data. Select scatter plot. Optional to add the trend line and format it, and this is the graph we got. And then interpret your results. That looks like it's normal. Notice that the R-square value of 98.61 tells us that about almost 99% of the variation can be explained by just standard variation you would get within a normal distribution. So that means this is very likely comes from a normal distribution. And if I do the standard deviation of that data set, remember it was about 6.3. And the slope of this regression line is about 6.3, 6.32, and the actual was about 6.35. So pretty close to the. This was the actual standard deviation. This is the slope of the regression line. Okay, whereas this is the mean, and that's also the y-intercept on the regression line exactly. Now, we want to do the same thing on our calculator. Okay, well, if you have a Inspire, it has a spreadsheet, so you can do exactly the same steps that we did in Excel, but it turns out you really don't have to, because the TI calculators, graphing calculators, have a normal probability prop built in. So it's much more simple on the TI-84, for example. Okay, so all you have to do is get your calculator, press Stat, and then choose number 1, Edit. Now I'm not going to erase the data because I already have it, but if you have some data in here, you can put your cursor on the top of the thing, where the label for the column, hit clear and enter to clear that column out. You want to do that for column 1 and then enter your data. Notice it does not have to be put into order. So this is in the order of the presidents. So this is George Washington, John Adams, Thomas Jefferson, etc. Last one being Barack Obama as of the date I'm doing this particular video. He's the current president. So I have the data in there. I've already got it typed in, but you just type 54, enter, 61, enter, and so forth. When you get all the data in, then we have it there. Now to set up the normal probability plot, we go to stat plot, which is second y equals. And I've got it in plot 3. But you can put it in any one of these 3. I choose this one. And notice I'm going to turn it on. And I'm going to choose this last one over here when it gets down to type. The first one's a scatter plot. We have a histogram, box and whiskers plots. The last one is a normal probability plot. So we select that. And it's going to ask us where our data is. My data is in L1. And for our data axis, do we want our data on the X or the Y axis? It'll do it either way. To do it the way that I'm doing here in these notes, we want the data on the Y axis and the expected z-scores on the x-axis. So we're going to choose Y and then the mark. So we should basically have it selected like this. Okay, and so you have that that demonstrated for you right there. Okay, now we've set it up, so we're going to quit second mode. Okay, and we're going to go to here. Notice that plot 3 is turned on. Also, I've cleared out any other graphing. Then I'm going to do zoom 9. Since I know it's 9, I can just press 9 at this point, but I'm going to go down arrows just to show you what it says. Zoom 9 is zoom stat. So I can just press 9. And it figures a window for us to see our plot. And this is the same plot that we got on the Excel. So just look at it. You can tell it's pretty close to being a straight line, so that says this is normal. Now if you want a reference line, the line that we're referencing should be this line here. Let's put it in. Well, before we can put it in, we need to find the standard deviation and the mean of our data set. Well, that's pretty easy. That's just one variable statistics. We know all about that. So we go to stat, then calc, one variable statistics for list 1, and calculate that. Yours may say one variable stats, then you do L1, which is second one, and then enter. And notice this tells us a lot of statistics, and down arrow for some more, but in particular it tells us the mean, x bar, and the standard deviation, which is S, since this is a sample. There will be presidents in the future, so this is not all the presidents ever. It's all the ones we've had so far, but just not all that we will ever have. And so it's still a sample, and so we use that sample standard deviation there. Now, what is the equation that we want? Well, it's S, which we can get by going to variables, number 5, statistics, and it's S sub x, which is number 3, times x plus, and we want x bar here, and so we go to variables, and we go to number 5, and it's x bar here. It's really y bar, but we did one variable statistics. It's going to store it as x bar. And so that should be the line that we want. So now if we hit graph, it's going to graph that line here. And of course, if it's normal probability distribution, the dots will be very close to this line, which in fact they are. Okay, so that's very close to a normal distribution. So our conclusion then is that this is actually a normal distribution. Now that last part of actually drawing the line is optional, but I did want to emphasize that by letting it set up the way we have done here, that slope and y-intercept do have some meaning for us. The slope of that line is the standard deviation of our data set, and the y-intercept is the mean of our data set. Another way we could do it is to go through and calculate the regression line. We should know how to do that, and that will give us a possibly slightly different line than this one, same y-intercept, but possibly slightly different slope, but very, very close. And that's also a good way to do it. Okay. Notice that if we hit trace, and we're here, negative 2.269, and then 42. Let's find that up here. If we go up here to our table that we have, where's our table? Okay, I don't have the table there. Let's actually put the table in there. From it, I have it over here in Excel. Let's take that table and put it in our notes. Okay, so there's the table that we have. And if we find 42, notice it's negative 2.269. And if you look at our trace, that's exactly the same one there. And if we trace over to the next one, at 43 for y, and negative 1.8134, and so forth. So notice that the built-in method is computing exactly the same ordered pairs that the method we did in Excel. So it's using exactly the same method. And that's all built in. Now, finally, let me note a couple of things here. Some statisticians use variations on this for the normal probability plot. For example, your textbook, the Weiss textbook that we're using this semester, uses tables to compute the predicted z-scores based on the ranks. So you rank the data, come up with the ranks, use the tables. It's the way the book tells you to do it. Well, it's doing a very similar thing that we're doing here, but instead of using the formula that we're using to produce that table, it's using a slightly different version to produce the table that's there. Okay. The other thing that they do is Weiss reverses the axes so that the x's are the data value and the y's are the probabilities. Now that's pretty easy to do here. If we go to, on the calculator, we go down here to plot 3, and we just make the choice of down here where it says data axis, we choose X instead, and then do a zoom 9. We get that plot instead. Now the bad news is, notice that you can't even see the line here that's going with it. The slope and y-intercept don't have these nice little meanings. So that's why I prefer the way we had it set up to begin with, so that the x's are the expected z's and the y's are the data values. So here it is, you kind of can see it with the labels. The expected z-scores are x's, and the age at inauguration, the actual data values, are the y's. Then the y-intercept and the slope have some meaning for us. In fact, well, that's one way we can kind of compute or at least approximate the mean and standard deviation, is by doing a regression line here and then working this out. Okay? So, if we're going to do this on our homework or whatever in this course, we're going to be using the method used by the TI-84, which is the method I went over of how to do in Excel. And we'll just use our TI-84 or similar calculator to do it, since it's already built in. So it's pretty straightforward to do. You just have to learn a few steps there, but it's very similar to how you do other types of graphing. Notice we didn't even have to come up with the ranks, we didn't have to come up with the z's, we didn't have to put our data in order. We just have to get it typed in, then choose the right kind of plot to plot it. Also, when you finish I'm going to go back here and do a couple things real fast. First of all, I'm going to turn this back around where the axes are like I want them, which is the data on the Y. So now when I graph, it'll be where we want it to be. Zoom standard, zoom stat. Now we get it where we want it to be. And when I'm finished, I always want to clean up. And particularly, I want to go up here and turn my plots off before I finish up here. And I don't necessarily need this, so I'm going to clear it out too. So kind of clean things up. And then I'm done with this. Alright, so that is how we can assess some normality with a normality or normal probability plot.